Yeah. Now let's consider for the zone boundary. There is an energy band gap near the zone boundary. Then in this case, we can calculate the central equation near the zone boundary. The title is the approximation near a zone boundary. Yeah, as we said, in the zone boundary is that in the energy dispersion relation, in here k equal minus a pi over a and pi over a. It is first zone boundary, first Brillouin zone. Here in this case, let's suppose that the potential is small in comparison with the kinetic energy near the zone boundary, and the potential is small with the kinetic energy near the zone boundary. And here the zone boundary defined that it is 1/2 g is that pi over a. And let's divide several cases. Two cases. One is that at the zone boundary, and the second one is near the zone boundary. First one at the zone boundary. Yeah, here zone boundary in this case, here we only consider at this region, these two region. Here because k equal to 1/2 g, the k square is that 1/2 g square. Then because of the translation symmetry, then by the k minus g, it is g is a reciprocal lattice vector. K minus g and k equal identical with each other because reciprocal lattice vector translation is the same as the original vector. Here k minus g square is that 1/2 g minus g, and also it is also 1/2 g square. Therefore, at the zone boundary is that 1/2 plus minus 1/2 g, as you know. In this case, let's consider central equation. Central equation is that lambda k minus epsilon ck plus summation for reciprocal lattice vector potential g c k minus g equal to 0. Here lambda k is the kinetic energy, h bar square k square. Here at the zone at k equal to 1/2 g case, it is a lambda minus epsilon c k equal 1/2 g, and also plus potential and c equal to minus 1/2 g equal to 0. It is the first central equation. In the case that the minus 1/2 g case, lambda minus epsilon c minus 1/2 g and the plus v c. Actually, in this case, k minus plus 1/2 g is that 3/2 g, but when we translate as a g reciprocal lattice vector, then I mean that it is a k minus g is that minus 1/2 g minus g, then it is the minus 3/2 g, but anyway, then the translation by the symmetry, for example, something like 2g is identical. Therefore, in this case, 1/2 g is equal coefficient at the 1/2 g equal to 0 because of the translation symmetry preserved. And here, because that's why we use that c 1/2 g and the c minus 1/2 g is that there are two unknown coefficients, c 1/2 g and c minus 1/2 g. It is two unknown coefficients, and two equations. Therefore, we can solve this equation exactly. Therefore, we can make the matrix, in this case lambda minus epsilon, and V and V, and C G half and C minus G half equal to 0. It is the matrix form. Therefore, in order to have the non-trivial solution, this matrix should not have the inverse matrix. Therefore, it is the case that two equations have non-trivial equation only in the case that this lambda minus epsilon v lambda minus epsilon, determinant of this matrix is 0. Lambda minus epsilon square minus v square equal to 0. Therefore, lambda minus epsilon equal to plus minus v. Therefore, the energy is that lambda minus plus and plus minus is identical. Therefore, here plus minus v. Here, and it is anyway, the energy difference, it is kinetic energy. And anyway, let me see that in this case that here the here h bar square and k square over 2m, and it is that h bar square k square is that at the zone boundary is that g half square plus minus v. Therefore, there is an energy difference between the high and low energy state. And in this case, at the zone boundary, the energy difference is that 2v. It is the energy difference between high and low energy. At the zone boundary. Here, from this equation and from the central equation, the ratio of these coefficients can be written like this: C minus 1/2 G over C 1/2 G is that from this relation epsilon minus lambda over V, it is plus minus 1. Therefore, these coefficients can be, the amplitude of this coefficient can be chosen as a unity. Therefore, Fourier expansion of the wave function at the zone boundary the wave function can be written like this: exponential I kx means that it is 2 half g half x plus minus exponential minus I k equal to minus g half x. Therefore, plus means that the wave function at the bottom of the energy gap, and minus means that wave function at the top of the energy band gap. Here, in this case, is the at the zone boundary. Secondly, let's consider near the zone boundary. Near the zone boundary, the wave function is not exactly written like this. Here, in general, psi x is that ck is the coefficient exponential I kx and plus c k minus g and exponential I k minus gx. It is a general expression of the wave function near the zone boundary. Therefore, also central equation also should be general. central equation lambda k minus epsilon ck plus vc k minus g equal to 0, and also lambda k minus g minus epsilon c k minus g plus v c k equal to 0. The two equations and two unknown variables, and in the same way, the determinant of this matrix lambda k minus epsilon and the lambda k minus g minus epsilon and the v and v, this determinant should be 0. Here, lambda k minus, not subscript, k minus epsilon, lambda k minus g minus epsilon minus v square. In this case, epsilon square minus epsilon, lambda k plus lambda k minus g plus lambda k minus g, lambda k minus v square should be 0. Therefore, from the second order equation, epsilon can be written down 1/2 lambda k minus g plus lambda k plus minus 1/2 square root lambda k minus g plus lambda k square minus 4 lambda k minus g lambda k minus v square. It is the solution of the energy eigenvalue. Then here 1/2 lambda k minus g plus lambda k plus minus, here when you consider it is a lambda k minus g square, lambda k square is simple, but here this multiplication in the two terms, 2 plus 2 lambda k minus g lambda k, but in this case minus 4 lambda k minus g lambda k. Therefore, the in the intermixing component is minus 2 lambda k minus g lambda k. Therefore, it is that 1/2 square root lambda k minus g minus lambda k square plus 4v square. Here, because near the zone boundary, then we know that this is a first Brillouin zone, and let's consider for the in between for k minus g minus here there is a energy in this case in general. Here is the k point, it is the k minus g point, but let's consider for the in between k minus g and k. Here let's define that k tilde is the k minus 1/2 g, then it is a k tilde, and the k tilde is that in between the k minus g and k point. Here then lambda k can be written down h bar square k square over 2m. Then it is that h bar square over 2m. K means that capital K tilde plus 1/2 g square. Then it is h bar square k tilde square over 2m plus h bar square k tilde g over 2m plus here in this case h bar square over 2m and also 1/2 g square is the final term. Here is that lambda square. Lambda square means at the zone boundary, the kinetic energy at the zone boundary. Here is the lambda. And also we should calculate lambda k minus g plus lambda k and lambda k minus g minus lambda k. Therefore, here lambda k minus g is that h bar square k minus g square over 2m. Then is that h bar square over 2m, because k minus g is that from this definition, and we can think that k minus g is that k minus 1 half g minus 1 half g, then it is a k tilde. Therefore, it is that k tilde minus 1 half g square. Then it is also can be write down h bar square k tilde square over 2m minus h bar square k tilde g over 2m plus lambda. Therefore, then this lambda k plus, we should calculate these equations. Here it is the epsilon. Therefore, this epsilon can be calculated. And also in this case, for the summation of the lambda k minus g and lambda k is that, and the negative term and the negative and positive cancel with each other, and the first and final term has a double term. Therefore it is h bar square k tilde square over 2m plus lambda. It is that plus minus. It is that for when we there's 1 half inserted in the square root, it is 1 half, and also lambda k minus g minus k is that. Anyway, this plus term, the first and final plus term cancel with each other, and only 2 times this second term. Therefore, it is that h bar square k tilde g over m, and square plus v square to the 1 half. Then, because this lambda has the h bar square over 2m has the same component, and h bar square over 2m is same component, and k tilde square plus, and also 1 half g square, and plus minus plus minus. Then let's calculate this term. Let's calculate this term. Then it can be write down 1 half. Let's write down h bar square over 2m, then g square over 4, and then h bar square k tilde square over m. Then it should be, here is a, should be 8. It is lambda, and therefore when it decomposes in this term like this, it is that okay. It is that can be write down like this, and 4 lambda and over h bar square k tilde square over 2m. Here it is 2 and also 2 plus v square 1 half. It is a little bit tedious, but it is straightforward. Let's suppose that the the potential is highly enough comparing with this term and h bar square over g k tilde over 2m, then we can expand this term. Then epsilon k tilde has the h bar square over 2m k tilde square plus g square over 4 and plus minus v. Then 1 plus or here this 1/2 in the approximation because the v is very high and the v extracted in the outside, and also 1/2 can be multiplied this term because this term is very small. Therefore here it is 2 lambda over v square h bar square k tilde square over 2m. It can be approximated like this. Therefore this it is a general formalism of the epsilon. Therefore let me see that at the zone boundary means that k tilde equal to 0, and because k tilde is defined by this k minus 1/2 g, therefore at the zone boundary k tilde equal to 0. Therefore in this case lambda is that epsilon plus minus plus epsilon is that h bar square over 2m g square over 4 plus minus v, and it is coincide with the energy difference at the zone boundary. When you draw this picture like this, the energy dispersion relation, and it is the zone boundary. It is 1/2 g. In other words, pi over a. The energy band gap, without consideration of the energy band gap, it should have the parabolic band structure because h bar square k square over 2m. But yeah, I'm sorry. Well, from this equation, there are two energy difference. At the zone boundary, there is the energy band gap, and also near the zone boundary, the energy dispersion may have like this, and it is epsilon plus and epsilon minus. And there is a energy band gap here. It is energy band gap is about 2V. V is interaction potential energy. Therefore, and in conclusion, the energy band gap at the zone boundary is the Bragg reflection of electronic wave at the zone boundary. And because when you consider that there is a periodic boundary condition, and also a periodic boundary condition is that when you think about that this kind of chain structure, and this one is a starting point, but it is the end point. Then when you consider this point, it is the going outside, but it is inside, and therefore there is the energy difference. And when you can think about that, and the translation, it is reciprocal lattice vector concept can be understood like this. And when there is in fly go outside, then the same fly goes out inside. Then this point and this point is identical, and the same with the translation symmetry. Therefore, at the zone boundary, the energy electronic wave function have the reflected, and because this point and this point in ongoing going outside wave function is same with the going inside wave function because of the translation symmetry. Therefore, there is an interaction between the reflected and transmitted wave electronic wave function, and it makes the energy difference. That's why it is the energy band gap. The cause of the energy band gap is the Bragg reflection near the zone boundary.